What we're going to synthesize is this complex here. Can you name that? Oh, all right, potassium, I seem to hear. Trioxalato. Chromium, 3? No. Trioxalato. Chromate, yeah. It's an anion complex, so we have to call it chromate. And then the charge is, you got the charge right, Tristan, it is 3. So potassium trioxalato chromate 3. No, we didn't have to use tris here. We didn't have to use tris because there's no di-tri in the ligand name. The ligand name is oxalato, and so there's no confusion there. This would just be 3 oxalates on the chromate, or chromium. Chromate's a bit confusing because there is the chromate ion. Can somebody remind me what the chromate ion is? This chromate is not to be confused with the chromate ion. Chromate has the formula what? CrO4 is correct. Charge? No, not minus. Yeah, -2. So should review those once in a while, the ions. Chromate is one that people often get wrong. Chromate and dichromate. So this chromate here has nothing to do with this chromate. They're two completely different things. This chromate is just chromium metal in a negative. It's a positive chromium ion in a negative complex. So it's a bit confusing. But this chromate is CrO4, 2-. The oxidation states are quite a bit different. The oxidation state of chromium metal in this complex is 3. And so we have a +3 oxidation state here. What is the oxidation state of chromium and chromate? +6. When we look at, let's take a look at the periodic table. Actually, let me pull up my periodic table here. If we look at chromium, what do you think the oxidation state on chromium ranges from what to what? +6 is the max positive, good. Well, negative, it would be kind of crazy. Negative, because it'd be -1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 to reach it out here. Do you think -12 is reasonable? No, -12 is not reasonable. So probably, and the metals in general don't have an anion. You know, And so we just say 0, like chromium metal would be 0 to +6, +6 being the max. So we expect chromium to range in oxidation state between 0 and +6. So if we see a +6 like this, what do we say? Well, we say it's probably going to be pretty electron poor. You know. And being electron poor, we'd probably say it's an oxidizer or reducer. Oxidizer. Now, whether it's going to be good or not is usually a little bit of memorization. What you do is you memorize some like reference points, and these reference points will just help you understand the chemistry of these things better. So chromium-6 is a pretty decent oxidizer. It's a good oxidizer. And so we note that it's a good oxidizer. Whereas, you know, some other things in the +6 might not be as good of an oxidizer. You know, so for example, if we had selenium in the +6 oxidation state, it's probably not as good of an oxidizer. You know, we'd have selenium in the +6 oxidation state in selenate ion, which is SeO4 2- here. And so it's not very strong. Even though it's at +6. Whereas chromium would be a stronger, you'd expect to be stronger. And these are just reference points that you kind of memorize. Like phosphorus +5, like in phosphate. Phosphorus in the +5 is not that great of an oxidizer either. So +6, +6 is kind of a high charge. And so it's not really, when we look at chromate over here, the chromium's not really +6. You know, that's its apparent charge. Apparent charge of assuming the bonding were 100% ionic, but the bonding is not 100% ionic. And so this is kind of the max charge here. And so sometimes we call these chromium Roman numeral 6. And so this tells us the valence or the oxidation state. Valence / oxidation state. So we see chromium-6 here in chromate. We also see chromium-6 in dichromate. This is also chromium-6. What am I doing here? I have my Roman numerals flipped. That's not 6, that's 4 that I just wrote. That's 6. So it's used in different things. You know, it's used in like, for example, in leather tanning. They use chromium-6, you know, as an oxidizer for leather. They use it in concrete. You know, my next door neighbor was pouring a concrete patio, and it was a really windy day, and then all this concrete powder ended up in my backyard. And I thought, oh boy, this is chromium-6 all over my backyard now. Chromium-6 has a bad reputation in California. Because it was found in drinking water supplies in the Central Valley. Yeah. There's a movie made about it called Aaron Brockovich. I don't know if you heard of it. It's quite some time ago. But they found one of these clusters, health cluster. I'm not sure, cancer cluster. I haven't watched the movie actually, so I've seen it. And so you should be careful. Just like gasoline, you have to be careful to minimize your exposure, because gasoline contains some carcinogens as well, mutagens, carcinogens. And the reason I'm going through this is because we're going to make this stuff, but what are we going to make it from? We should make it from chromium-3, correct? Because we need chromium-3 in order to make this, maybe chromium-3 chloride. But we're going to make it from chromium, either chromate or dichromate. Actually, chromate and dichromate are related to one another. And it depends on the pH, which form you get. And so there's a kind of an interesting acid-base reaction that interconverts the two. So if we have dichromate, oh, dichromate, I screwed up too. I don't know. This is the time changes. I don't, fortunately. Dichromate is not Cr2O6, it's not Cr2O8. What is it? 07. I talked about this in Chem 1A. Does anybody recall what happens when you link up two chromates together? You'd like to attach the two oxygens, because it's tetrahedral. So you want to attach the two oxygens together, but you don't, because oxygen-oxygen single bonds are extremely... Those are called peroxide bonds. So what happens is we lose one of the oxygens in order to link them up. And so you have a chromate here, and so it goes chromium, oxygen, chromium. And so that means it's not perfectly two chromates, it's two chromates minus one oxygen. In order to do that, there are different ways we can look at it. Actually, let me go this way. I'm going to link up two chromates to make a dichromate. And so this is going to be the dichromate chromate. So if I try to link up two chromates together like this, I'm going to have to lose one of those oxygens, because I don't want a chromium, oxygen, oxygen, chromium bond, because these bonds have, I think, well below 100 kilojoules per mole. I think they're around 67. Actually, what is a peroxide? I don't have it memorized. It's like 60 to 80 kilojoules per mole. Just have the range, but it would be interesting to see what an we call these bond enthalpies or bond energies. Actually, 146, that's pretty good. That's pretty decent. But it's very weak. 146. Well, what do bond enthalpies range from? This is quite weak. To give you an idea of bond enthalpies, does anybody remember how strong hydrogen bonds are? Hydrogen bonds are not really bonds. These are, IMFs. And these are the stronger intermolecular force. Roughly. These are like reference points, little reference points to help you remember. Like, so for example, if you move to a new town or new city, you want some like reference points so that you can remember where you're at. And so these are little reference points so that we know where we're at. We're not lost in a sea of numbers. We know kind of what the numbers mean. And so hydrogen bonds are about 25 kilojoules per mole, but that's not even a real bond. And so the very weakest bonds are going to be, I mean, this is only, what, 5 times? No, 6 times stronger than a hydrogen bond. You know, that's not much. And so bond energies range from about 100, less than 100. I think there's maybe a weaker bond would be the iodine bond is pretty weak. And yeah, this is around the weakest. The problem is visible light can break this bond. You know, light can easily break this bond. And so we have to protect this from visible light. So that's very weak. So when we form it, we have to get rid of an oxygen, but how do you get rid of an oxygen? And this is like, these are like patterns that, you know, it takes time to develop or to remember sometimes, these patterns. But have you seen this before? Maybe. Let's take a look at some of these here. So for example, nitrate. If you look at nitrate, there's 3 oxygens here. But when we look at nitric oxide, there's only 1 oxygen here. So we lost 2 oxygens. Now where did those oxygens go? So we start off with 3 oxygens, we end up with 1 oxygen. Where did the other 2 oxygens go? Rebecca? Yeah, they paired up with hydrogen to make water. And in fact, we're losing the oxides. We lost 2 oxides, so we need 4 H pluses, and then we'll make 2 waters. Do you see this pattern repeated over and over again? Here we have 3 oxygens, but we end up with no oxygens here. What happened to the 3 oxygens? Yeah, they paired up with, well, we have 2. But altogether, 2 times 3 would be 6. 6 oxygens will need 12 hydrogens to make 6 water. And you can see this pattern over and over and over again. So if you read this table once in a while, then you would have been, oh, it's easy. We can get rid of the oxygen. How do we get rid of the oxygen? Yeah, we're going to pair it up with H pluses. And so we'll take one of the oxides, pair it up with an H plus. So this is what I'm going to do. I'm going to take 2 chromates over here. These are patterns that you can see just by, you know, you don't really memorize it. You just look at the tables and read through it once in a while, and then you'll see these. So in order to pair these up, I want to get rid of one of these oxygens here because this peroxide bond's weak. If I can eliminate one of those oxygens, then I can make a dichromate that looks like this. And that's going to be a much stronger bond here. You know, tell me what the strongest covalent bond you can think of. What's the strongest covalent bond you can think of? These are like little reference points again. You'll want to know. It's very common. Extremely common. Everyday chemical. It's an extremely common everyday chemical, but it's so unreactive because the bond is so strong that we completely ignore it, usually. You never really think about it at all. Yeah, N2. Air, I mean, each breath you take is 80% nitrogen. Do you ever think about the nitrogen you're inhaling? You never think, you think about the oxygen but you completely ignore the nitrogen because the nitrogen is about 1,000 kilojoules per mole. So it's easy to remember the reference points. The reference points are bonds range from 100 to 1,000 covalent bonds, from 100 to 1,000 kilojoules per mole. On the 1,000 kilojoule per mole end, this is so unreactive, this is called a pseudo-inert gas. It's a pseudo-inert gas because it's hard to react nitrogen with anything, you know. Whereas something like this peroxide bond is very reactive, extremely reactive. Let me give you an example of how reactive these are as a reference point. This is Chem 1B. I kind of ignored this in Chem 1A. But let's take a look at number 3. What is number 3 on the top oxidizers? If we look at number 1, everybody should know number 1 oxidizer is fluorine. Is this the most powerful oxidizer in the universe? No, it's not. Can you think of another oxidizer that's more powerful than fluorine? Way more powerful than fluorine. Some people have to worry about this oxidizer around LA. Here in Torrance it's not so bad, but if you're like Pacific Palisades, Malibu, Palos Verdes, you might worry about it a little bit. Anybody? Not hydrogen, it has to do with helium. But we don't call it helium, we call it what? Well, radon is not it. Radon is it's a product of the radioactive decay of radon. It's a helium nucleus. The helium nucleus we call alpha particles. Did I talk about alpha particles? Alpha particles are way more powerful. And radon's dangerous because it emits alpha particles. And radon's especially dangerous because you inhale it. And as it emits alpha particles, those alpha particles are going to start oxidizing your lungs or whatever else. And too much oxidation can cause, the oxidative damage and lead to cancer or whatever. So fluorine's not the most powerful in the universe, but it's the strongest on this chart for sure. What's below fluorine? What's below fluorine is ozone. Ozone is what we call an allotrope of oxygen. Allotrope just means a different form of the element. O2 is another allotrope. O, atomic oxygen, is another allotrope. Ozone. Ozone is a strong oxidizer as well, in combination with H+. What's number 3? Well, number 3 is kind of weird because you haven't learned how to name this, have you? Maybe it's like I don't know, thio something. Like S2O3. S2O3 2- is thiosulfate. but it's not thiosulfate. It's something else. This one, you know what it looks like? It looks like two sulfates attached. But anyway, what's the oxidation state of sulfur here? Yeah, oxygen is -2. -2 times 8 is -16. -6 plus what gives us -2? -16 plus 14 will give us -2. So we have plus 14 distributed over two sulfurs. That means each sulfur is +7. And so sulfur is +7. Well, what's the normal range for sulfur? Not +5, +6. +6 to -2. So it's +7, which means we must be ionizing a core electron. So automatically it's very weird. I mean, it's unusually high. And have you ever seen anything outside the range? No, and what it turns out, it's not outside the range. You know that sulfur is +6? We have to look at the structure. The sulfur is +6. It turns out the oxygens aren't all -2. 6 of the 8 oxygens are -2. 2 of the 8 oxygens are -1. Where does that -1 come from? And so looking at this particular structure, this will just be another side topic here. I'll come back to what I was talking about earlier. It has a very weird structure. So we do the oxidation states here. These terminal oxygens are all -1. Or not -1, sorry, -2. Sorry, -2. -2. How about the bridging oxygen? Well, let's count it. The bridging oxygen has 2 lone pairs. Those lone pairs belong entirely to the oxygen, so that's 1, 2, 3, 4 electrons. And then it's winner take all. Oxygen versus sulfur, who wins? Oxygen wins. Oxygen versus oxygen, who wins? It's a tie. And so we end up with 1, 2, 3, 4, 5, 6, 7 electrons. Oxygen should have 6 electrons. It comes out to -1. So we have these -2s, and then this -1. This is another -1. And these are -2. What's the oxidation state on sulfur? Each sulfur is +6. Here. Okay. So what this is it's a peroxide. And so the name of this has some kind of peroxide in the name. It's like disulfate peroxide or something like that, which is quite a bit different than dichromate. Dichromate's more stable. This is less stable because of the peroxide bond. actually wrong chart. Let me show you this. Underneath this disulfate peroxide thing is what? Hydrogen peroxide. And hydrogen peroxide has hydrogen is the +1, oxygen is the -1. When it comes to assigning oxidation states, we always do hydrogen, the alkali metals, and the alkaline earths first, because those are going to get the charge. And so if hydrogen goes +1, then oxygen must be -1, that's peroxide, and oxygen wants to be -2, like in water. So hydrogen peroxide is a good oxidizer. But hydrogen peroxide is a weird one because, you know, oxygen can vary from -2 to +6. And so what that means is hydrogen peroxide can go both ways. It can either be an oxidizer and gain an electron for each oxygen to make water, or hydrogen peroxide could actually be a reducer. That is, hydrogen peroxide can actually give up electrons. And so hydrogen peroxide is a weird one because everybody, when they think of hydrogen peroxide, they think of powerful oxidizer. It is a powerful oxidizer. But what they don't realize is it could also be a reducer. What you would need is you'd need an oxidizer that's quite powerful to get this to react. But here, if the oxygen loses an electron, it can form oxygen 0 or O2 gas. So hydrogen peroxide, like water, can go both ways. It's just a much better oxidizer here than it is a reducer. You know, it's kind of weak as a reducer, strong as an oxidizer. Here. All right, so what we're going to do is in the synthesis we're going to be using actually chromate or dichromate. It doesn't really matter because what happens is these two interchange. Chromate and dichromate are kind of the same thing. They're kind of the same thing because of this. If I have two chromates, I want to get rid of one oxygen because I have 8 oxygens total now. So how can I get rid of one of those oxygens? I'm going to add what? If I want to get rid of one oxygen, how many hydrogens do I need? Well, one oxygen requires how many hydrogens? Well, let me give you the answer. 2. Because I want that to convert to H2O. Okay, is this working now? Yeah. So what I end up with is I end up with dichromate plus H2O. Now I'm going to use Le Chatelier's principle. They're in equilibrium with one another. And so I'm going to use Le Chatelier's principle. If I increase the H plus, what side is favored? The right side or the left side? The right side. And so dichromate is favored. Dichromate, do you know what color dichromate is? It's orange. And so if I increase the H plus, that means at low pH, I should have dichromate. However, if I decrease the H plus, what side's favored? Left side. So chromate is favored. Chromate is yellow. Dichromate is orange. And so at high pH, chromate is favored. So, you know, it's just changing the acidity of the solution. By changing the acidity of the solution, you interconvert. And so both of these are chromium-6. But in redox, I don't care if it's chromate or dichromate. It's chromium-6 that's important, right, in redox. It's the oxidation state that's important. And so both of these are going to behave the same in terms of redox because they're both chromium-6. So I'm going to, actually, can somebody see what the bottle, what do we have? Do we have chromate or dichromate back there? Or maybe it's in the hood or somewhere. Oh, there. We have dichromate. What color is it? Well, should be kind of orangish. Yeah, orangish. All right, good. So we're going to start off with dichromate. Now, what we want is we want chromium 3, right? Dichromate is a strong oxidizer, so we got to watch out. And are you guys familiar with the SDS or MSDS? It's now the SDS. I'm sure we're going to use potassium dichromate, but each chemical you buy, like say we buy that from Aldrich or we buy that from some other chemical company, they're always going to give us a safety data sheet. And so if you want any safety information for these chemicals, we go to the safety data sheet here, and then we can read this here. Welcome to Acrobat. So we're going to be using potassium dichromate. Uses laboratory chemical synthesis of substances. The company, they have a 24-hour emergency line. Let's say you inhaled a bunch of dichromate or you ate some dichromate or something, and you want some immediate, what should I do? Should you drink milk, or should you drink water, or should you drink nothing? So there's a 24 hours a day, 7 days a week, 365 days a year emergency phone number you can contact for any kind of emergency with potassium dichromate. One, we know already it's going to be an oxidizer, and it's a solid. So that solid is probably 98% pure. To buy the 100% pure stuff is expensive, and they get it close to 100%. It's not quite 100%. It's like 99.999, and they analyze it. It's called characterization to make sure it's fairly pure. And so we buy the lower grade stuff, the technical grade. Technical grade is maybe 97, sometimes it's 95%. There's other contaminants in there, but it's a lot cheaper. And so most of our synthesis is using technical grade. The top stuff is called analytical grade. Actually, it's not the cheapest. Food grade chemicals are cheaper because there are lots of other things in there. They don't need it as pure. So food grade. Pharmaceutical grade's pretty high purity, but the top purity level is analytical grade, because analytical grade, we try to get it as close to 100 as possible. So don't eat it. So that's oral toxicity, and don't inhale it. So it's a fine powder. So try not to create a dust cloud. In fact, I'm probably going to move it into the hood. So in case somebody creates a dust cloud, it gets sucked out the hood rather than you inhaling it, right? Because what we want to do is we want to minimize exposure. It's not like, you wouldn't take a tank of gasoline, which is carcinogen, and then open it inside your bedroom and then sleep at night with the gasoline fuming out of a tank, would you? No. And so this is the same thing. We just make sure we have certain precautions to make sure we're safe. So acute toxicity, skin corrosion, serious eye damage is category 1, which is the worst. Or I don't know how bad. Respiratory sensitization, skin sensitization. So people who work with this a lot are going to have really, they're going to develop a sensitivity to it. So much so that, there's some chemists, one of the chemistry professors here developed sensitivity to hydrochloric acid. So they couldn't breathe this stuff. Whenever they got around hydrochloric acid, it was painful for them. And this is because of this exposure. They developed this sensitivity to it. But we're just going to be very careful. It's a mutagen. We have to be careful of that. It could cause like birth defects or stuff like that. Carcinogen, reproductive toxicity, target. And so what you want to do is you just want to handle this with care. In other words, you don't want to create a cloud of it, and you just want to make sure it's contained. You know, if you read the MSDS for gasoline, it's kind of like this, except gasoline's not an oxidizer. Gasoline's a reducer. It's a fuel. You know. And so it's not that you can't handle it. You just have to be very careful in handling it. And so this O means oxidizer, and it can cause fires, being a strong oxidizer. And this obviously is health risk, corrosives, inhalation hazard, caution. This one, actually, I don't know this one. I'll have to look that one up. But you can just read it here. May intensify a fire, etc. Yeah, you want to wear protective equipment. Wear respiratory protection in case you create a dust cloud. So that's why I'm going to move it into the hood. Use gloves. If swallowed, immediately call the poison center. If swallowed, rinse mouth. Do not induce vomiting. If on skin or hair, take off immediately all contaminated clothing. Rinse skin with water, shower. You know, we have showers. We have a shower in the corner here. The pull-down handles against the wall. We have that shower. We have handheld showers at the sink that pull out on the rubber hose. Have you seen those? Those double as eye washes. So we have eye wash here, eye wash there. So if any gets in your eye, you want to immediately wash it out, but it shouldn't as long as you're careful. We also have a private shower, you know, as well inside behind the lecture rooms there. That's, yeah, if it gets on your clothing, you don't want it contacting your skin, so that's why they say it. Etc. So sometimes they give toxicity data here. Sometimes they give the LD50. Have you heard of the LD50? The LD50 is like acute toxicity. How much you'd have to eat or how much you would give the population if 50% were to die from poisoning, you know, etc. So this is quite a lot of data here. So that's the chromium-6. So we need to be careful with this, and it is a powerful oxidizer. It can be explosive. Here, actually, I should show you that. One last thing here. Possibility of hazardous reactions. Risk of explosion with good reducers. So if you put iron, iron's a good reducer. You'll get an explosion, potentially. Magnesium is even better. Hydrazine is a good reducer. These amines are good. Amines have nitrogen, electron-rich nitrogens. Ammonium has electron-rich nitrogen, although nitrate is not. Ammonium is a good reducer. Boron, acetic anhydride, these are all good reducers. Reducing agents. Sulfuric acid, that's weird. Here, silicon, anhydrides, phosphides, sulfides are really good. Nitrides, yes. Fluorine's not a great reducer, but you know, this is kind of a random list. Well, we're looking at reducing agents, so we have to be very careful. It's a strong oxidizer. That's telling us. Strong oxidizer, but we don't want chromium-6. You know, what do we want here? In our compound, we want chromium-3. So that means we have to use a reducing agent, but if we have to use a reducing agent, I don't want an explosion to occur, right? And so the first reaction that we're going to do is we're going to reduce dichromate using a reducing agent. But do we want to use a good reducing agent or a poor reducing agent? we want to use a pore reducing agent. A pore reducing agent would be something that doesn't burn so easily. And the compound we're going to use as a reducing agent is this. What is this called? C2O42 minus. Oxidate or oxalate? Oxalate, yeah, that's good. Just oxalate. When we look at the redox, we care about the oxidation state. What's the oxidation state on carbon here? +3? Yeah. Which means when we look at carbon, carbon's oxidation state ranges from -4 to +4. So at +3, we're almost at the end here. And so you'd expect oxalate to be a oxidizer, but it could go either way. You know, it's on the electron pore end of the spectron. It's on the electron pore, but it does have one more electron to give. And so I would think of this oxalate as being a reducer, or not. Actually, I'd think of it as being an oxidizer on the electron pore, but can also be a reducer because it has one more electron. If it's going to be a reducer, do you think it's going to be a very good reducer or a poor reducer? Yeah, we'd expect it to be a poor reducer. It's going to be hard to burn. Well, this is what we're going to use. We're going to use a pore reducer. We're going to use, this is going to be our reducing agent. Now, if we use oxalic acid or potassium oxalate, does it change the oxidation state on carbon? No, and so we expect the redox properties to be similar. So we could use either of these. We're going to use oxalic acid, maybe some potassium oxalate in this form here. Okay, from this. So essentially what we're going to do is we're going to take our dichromate, and dichromate, was that the acid form or the base form? What color? Okay, let's take a look at dichromate again. Is dichromate the acid form or the base form? In other words, which one is more stable in acid? Chromate or dichromate? Dichromate. And so that's what we call the acid form. Whereas chromate would be the base form because that's what's most stable in base solution. And so this one is going to be, what we do here is I'm going to just put this here. I'm not going to balance this equation. We'll balance it later. But essentially what we're going to do is we're going to use oxalate either in the form of oxalic acid or potassium oxalate, actually in both. And then we have oxalic acid present, so there's going to be some H+. So we're going to say that we have oxalate and H+ present, and then we're going to reduce this to chromium 3+. All right, so this is step one. Step one, if you read the instructions, it says to slowly add the oxalic acid. Oxalic acid is a solid. We're going to use that. To slowly add the oxalic acid. Why? Why not just dump it all in at once? The reason I'm asking you this is because every semester somebody dumps it in all at once. Why don't we want to do that? The thing is, if you have a powerful oxidizer, dichromate, and you have a reducer, what could happen if you get too much reaction too quickly? You can have an explosion. And so every semester somebody dumps it in all at once, and fortunately it doesn't explode like a violent explosion because oxalate's not that great. But what happens is it explodes in a foamy mess all over the bench, so they got a lot of heat generated and all these bubbles and then splatters everywhere. And so hopefully that doesn't happen. This semester, people will add it slowly, and then let the reaction, if the reaction starts to get violent, you don't add any more. Let it subside and then add a little bit more. Reaction kicks up. And then just controlled addition of oxalic acid. Okay, we're almost there. So this is a redox reaction. And then in step 2, what we're going to do is we're going to do our Lewis acid base. Our Lewis acid base reaction is just chromium 3 plus our ligands. How many ligands do we need? We need 3 oxalate ligands, and then we're going to form this. Charge on this is what? 3 plus 3 minus 6 is 3 plus. Or 3 minus, sorry. 3 minus. Well, this is easy because we already have oxalate present. So all we need to do is we need to add excess oxalate, and then we can take care of 2 reactions with 1 or 2 reagents. We're not going to add oxalic acid, the entire thing, because we also need what? Some potassiums in there. So we're going to use a combination of these here. And that's going to carry over here. This is primarily going to be the potassium oxalate. This part here. Step 3. Is going to be metathesis. In our metathesis, what we want is we want to take 3 potassiums that are floating around. There's lots of potassiums around this. So we're going to take 3 of the potassiums, and we want that to precipitate out with the complex. But there's a problem. Potassium salts are all soluble in water. They're soluble in water, so what we're going to do is we're going to do a process called solvent exchange. You heard of chemical exchange, right? The solvent exchange is, what we're going to do is this. We're going to take water and then add so much ethanol. ETOH is the abbreviation for ethanol. That we're going to change the ratio. Originally it was all water. And then we're just going to keep adding ethanol, ethanol, ethanol. And pretty soon the percentage of water is going to shrink and shrink. So the more ethanol we add, all the water is still there, but the more ethanol we add, the more ethanol-like our solvent is. Okay. And so we're going to add excess ethanol here. And then not only that, we're going to cool it down in an ice bath. Cooling it down in an ice bath is going to decrease the solubility. And so what we're going to do is we're going to precipitate this out as K3. solid. This is going to be PPT. It wouldn't be a PPT in water, though. It would be a PPT in ethanol, because the solubility of this complex is a lot lower in ethanol. Ethanol is a bit less polar than water. When we precipitate out, we want to precipitate out slowly. We want to precipitate out slowly, and so we're going to kind of add the ethanol slowly. The reason we want to precipitate out slowly is so that we can grow crystals. Have you ever grown crystals before? So slow growth is the best for crystals, because if you have rapid growth, what you end up with is a bunch of tiny crystals. We don't want a bunch of tiny crystals. We want a few big crystals. And so we'll talk about crystal growth more when we get closer to there. But when you do add the ethanol and ice bath, if it doesn't all precipitate out rapidly, that's fine, because we want it to slowly precipitate. In fact, we're going to give it a couple of days to precipitate. Okay, any questions on this? So I think what we'll do is we're going to have people work individually on this. That way you can grow your own crystals. You can see how the crystals come out. And I think we want a hot plate too. So I'm going to get some hot plates so we can cook things on. But take a look. It's just the synthesis of the chromium complex. I'll stop here.